Okay, so let's work some problems here where we can find the center of mass of a lamina using double integration. So our first problem here, we're going to find the center of mass of the region bounded by 0 less than or equal to x less than or equal to 2 and 0 less than or equal to y less than or equal to 3 with density equal to x squared. So let's go ahead and draw a picture of our bounded region, which is a very simple one. What we've got is x is bounded by x equals 0 and x equal 2, which is this line here. Y is bounded by y equals 0 and y equals 3, which is this place here. And so our bounded region is this area in here. So let's go through and do our calculations. Remember that the mass is the double integral over the region of dA, of course, times the density. So this is going to be the double integral of x squared. And here we actually do have a choice whether we choose to do x squared, dx dy or dy dx. And being that there's x's in there to start with, I'd probably do it as a dy dx. And so what this means is as we come down from the top, the first thing I hit is y equals 3, and then I go to y equals 0. And then take your bounded region, drag it to the x-axis, and you'd be bound from 0 to 2. So this is going to be the integral from 0 to 2, again working from the inside. The x squared carries down. When we integrate dy, we just get y, which we can look at between 0 and 3. And when you put those bounds in, you just simply get the integral from 0 to 2 of 3x squared dx. Integrating this is just going to give you x cubed, which you can look at between 0 and 2. So we get the mass of our system is simply equal to 8. Let's go through now and calculate the moment about the y-axis. And the moment about the y-axis is simply going to be the double integral of that region. In other words, just the mass times the x-coordinate. So it's just times x dA. And so we're not going to reinvent the wheel on this. This is going to be the double integral, and we will use the exact same thing we did before. That is, we're going to do the x squared, and I will still do a dy dx, but I need to come in here and multiply through by another x. So again, I'm going to work from the inside out. This will give me the integral from 0 to 2. Combining those x's, that's going to give me an x cubed. Integrating dy, I get y, which I can look at between 0 and 3. And then, of course, this gives me the integral from 0 to 2 of, looks like 3x cubed dx. And so then integrating that, we're going to get 3/4 x to the 4th, which we can look at between 0 and 2. And I do believe that this will give us the value of 12. Okay, so let's go ahead now. I'm going to need another sheet of paper here. And let's go ahead and calculate then the moment about the x-axis. And as we saw before, this is simply the double integral, or the mass, the double integral over the region R of lambda times the distance away from the x-axis, which is simply y. And once again, we're not going to reinvent the wheel. So this is going to be the integral from 0 to 2 of the integral from 0 to 3 of x squared. Of course, dy dx, that's your little m, times y. And again, we'll work from the inside. So this is the integral from 0 to 2, bringing down the x squared. When I integrate y, I'm going to get 1/2 y squared, which I can look at between 0 and 3. And so that just gives me the integral from 0 to 2 of what looks like 9/2 x squared dx. And when we integrate that, the 9/2 comes down. Of course, I'm going to get 1/3 x cubed, which I can look at between 0 and 2. And I do believe that this one is going to give me then 3/2 times 8, which is going to give me 12 as well. So then we have our three values here. We once again calculated little m to be equal to 8. The moment about the y-axis to be equal to 12, and the moment about the x-axis to be equal to 12. And so then remember, your x bar, y bar is the moment about the y-axis divided by the mass of the system, moment about the x-axis divided by the mass of the system. So that looks like 12 over 8, 12 over 8, or the ordered pair 4/3, 4/3. thirds. And as always, remember that when you get your center of mass, the one thing that you want to always make sure of is that that center of mass is at least sitting within your bounded region. It is not necessarily going to be the geometric center, and it shouldn't be, because remember, when we looked at this, we saw that our density was x squared, so that the higher we got to the larger values of x, the thicker or the greater the density was. And so if we look at this, it is actually 4/3, 4/3. So the center of mass is sitting right about here. Again, one thing we want to just make sure of is that we are at least within that bounded region. All right, let's look at our second example here. In our second example, we're going to look at the bounded region x squared plus 1, x plus or minus 1, and y equal 0. And then we've got two different densities to look at. So let's start by graphing our bounded region. And the only curve I have is this y equal to x squared plus 1, which is a parabola. And if I do a quick little xy chart using the values of x or the values in between all those values, I'm going to use -1, 0, and 1. For -1, I get 2. For 0, putting it back into this equation, I get 1. And when I put in 1, I get 2. So what I have then is the region that is bounded by the following. We're going to sit between x equal 1 and x equal -1. Our parabola, which has the coordinates, let's see, -1, 2, 0, 1, and 1, 2. So here is our parabola, y equal to x squared plus 1. We're going to be bounded by that. We're going to be bounded by the lines x equal positive and -1, and also y equals 0, which is going to be here the x-axis. So our bounded region is this region in here. Now, I've got two different densities there, and I want to look at how things change with both of these densities. The first one, notice, is a uniform density. And since we have a uniform density, again, thinking about it as thickness, the thickness is the same throughout, then I would expect in a uniform density for my center of mass to be the geometric center of this thing. And I do know that at least one part of this holds true, that if it's a geometric center, it's got to be somewhere along that line. To be a point somewhere along that line means that the x bar coordinate has to be equal to 0. And since x bar is equal to the moment about the y-axis divided by the mass of the system, and the only way a fraction can be 0 is when the top is equal to 0, I know that the moment about the y-axis for this will be 0 as well. And as a matter of fact, when you do this calculation using the fact that mass is equal to 2 times the double integral over my region, and notice I can bring the 2 on the outside here. That's my density. It's a constant, so it doesn't necessarily have to be on the inside. You can move it on the outside. And the dA, looking back at my picture, I really cannot do a right to left, because if I do it, I'm fine in here, but when I get up in here, the right and the left has a space in between. So I would have to split this into two integrals. So I really need to do this as a dy dx. Coming from the top, I'm going to hit the x squared plus 1 and go down to the y equals 0, and then we'll be bound between -1 and 1. Of course, then your moment about the x-axis is simply going to give you you're going to use the exact same integral, but you're going to multiply it by y. And when you do this, you're going to get a center of mass of, it looks like that one is going to be, here it is, 0.7, which actually makes sense, because it again, we would expect it to be sitting here on this line as long as the density is uniform. So here again, symmetry plays a big part in the fact when we have a uniform density. However, when the density is no longer uniform, in this case it's equal to x plus 2y, we can no longer use symmetry. And so here, when we calculate little m, I don't get to take my density and pull it to the outside because I have x's and y's in it. So it will still be the double integral from -1 to 1 of 0 to x squared plus 1. And I can still use the dy dx, but my lambda here is going to be x plus 2y. For the moment about the y-axis, we will simply add an x in the front of that. For the moment about the x-axis, we will simply add a y into the front of that. And for this one, we get our center of mass to be the ordered pair 2/7 and 48 over 49, which actually, if you look at that, that's about what, about 2/7 is about right here, and then right under 1. So the center of mass is still within that bounded region where I would expect it to be. But since the density is not consistent throughout, remember, if you think about it as thickness, the higher the x and the y values get, the greater the density, then you're going to have to be moving around to get that balancing point. So I'll let you work that out. You got the answers to that one. Let's go ahead and just look quickly at our last example. And the reason I wanted you to see this example is because notice that the only curve that I have in my bounded region is the circle x squared plus y squared is equal to 9, which means that I have a circle of radius 3. And of course, anytime our bounds are circular, it lends itself to switching this thing over to polar. So how would that work? Well, remember, little m is going to be the double integral of my density, which in this case is xy dA. Now, let's see, what does our region look like? By the way, I didn't even actually finish that out. Y has to sit between 0 and the top part of this curve, which means only up in here, but then x has to be greater than or equal to 0. So it looks like I'm dealing with that quarter of the graph. So to switch this over to polar, remember that x gets switched over to r cosine of theta, y becomes r sine of theta, dA becomes r dr d theta, and r will be bound between 0 and 3, and theta will be bound between 0 and pi over 2. For the moment about the x-axis, it was the double integral of this times y, so that's xy squared dA. Again, to do that conversion, we're not going to reinvent the wheel. We're still going to use x of r cosine of theta, but the y will be squared. So we will square this one times r dr d theta. And likewise, for the moment about the y-axis, it is the same thing as the mass times another x. So that's x squared y dA. Again, 0 to pi over 2, 0 to 3. This time it's the x that's squared, so that is r cosine of theta squared times r sine of theta times r dr d theta. So as always, anytime we're doing double integration when we have circular bounds, we can switch those over to polar.